I am very excited for this opportunity to talk to you about quantum computing and more specifically about quantum machine learning. This is because the time to get started in quantum machine learning is now. My name is Frank Sickert. I am the CTO of a small physics startup in Germany, and we serve clinical customers in the field of radiation protection. Moreover, we explored to what extent we can use quantum computing and in detail quantum machine learning for this purpose. And today I'd like to share some insights on why I am convinced that now is the time to get started with quantum machine learning. But first of all, if there were two terms in computer science that I would describe as overly hyped and poorly understood, I would say machine learning and quantum computing. And well, quantum machine learning is the use of quantum computing for the computation of machine learning algorithms. So could it be any worse? There are many anecdotes about these two technologies. They start with the machines that understand the natural language of us humans, and they end at the advent of the artificial and general intelligence that either manifests as the Terminator-like apocalypse or the WALL-E-like utopia. But don't fall for the hype. Instead, we need an unbiased and detailed look at technology. Let's start with machine learning. Machine learning is a thing labeler, essentially, says Casey Korzakov, who is the chief decision scientist at Google. So with machine learning, we aim to put a label onto a yet unlabeled thing. So here's a picture. Is it a cat or is it a dog? Sound easy, right? Labeling things is something we do every day. Distinguishing between cats and dogs is an easy task for us humans. In order to let a machine take over this task, you need to program it. You need to specify exactly how to execute every single step. The problem is, though, while we can do it, we don't know the exact rules of how we do it. The problem is, nature gave us abilities without letting us know how these abilities work. Apparently, the ability itself has been an evolutionary advantage, whereas the knowledge of it didn't. With this inability to tell a machine how to tell the difference between cats and dogs, what do we do instead? We treat a computer like a little kid. I have a two-year-old son, and he struggles with the words cat and dog. In his defense, the German words are Katze and Hund. These are a little bit harder to learn, but whenever he sees a cat, he says meow, and when he sees a dog, he says woof woof. So all we did was repeatedly tell him. Whenever he identifies a cat or a dog correctly, we reward him by agreeing. In case he's wrong, we correct him. So even the slightest difference in the feedback we give to our child will make him improve because he subconsciously optimizes his behavior for a reward. And that's exactly what we do in machine learning. Instead of specifying the details of how to do the task, we present correctly labeled examples to the machine and say, figure it out yourself. A major difference between teaching a child and teaching a machine is the underlying model. We humans keep our knowledge in our brains. It consists of myriads of connected neurons that form a network. Our senses feed electrical impulses into this network, and the output translates into our thoughts, into our commands to our muscles. As a teacher, we can't control how the brain of our students work. When we train a machine, though, one of our main tasks is to come up with a model that is sufficiently complex to keep the knowledge we want it to learn, but sufficiently simple to be trainable in a reasonable time. The model has a structure. It can be anything from a simple mathematical formula to a network of artificial neurons. And the model has parameters. These are trainable parameters. These two things determine the complexity of our model. Generally, the more parameters our model has, the better it can perform tasks, but the harder it is to train it. An algorithm that tells cats from dogs may work with a few thousand parameters. You can train it on your laptop. That's easy. But machine learning algorithms become increasingly hard to train. Let's take the generative pre-trained Transformer 3, in short GPT-3 for example. GPT-3 produces human-like text. It has round about 175 billion parameters. Training the GPT-3 would have required 355 years on a single GPU and cost $4.6 million. Of course, through parallelization, the training was much faster. Yet it took a tremendous amount of computing resources and therefore money. This is where quantum computing may come in handy. Quantum computing is a fundamentally different form of computation, and it promises to solve problems we couldn't solve with classical computers ever. But what makes a quantum computing so powerful? That isn't its processing speed. A quantum computer is rather slow in terms of clock speed. And what makes quantum computing so powerful isn't its memory either. It's absurdly tiny. We're talking about a few quantum bits here. What makes quantum computing so powerful is the algorithms it makes possible, because these algorithms exhibit different complexity characteristics than their classical equivalents. To understand what that means, let's have a brief look at complexity theory. Complexity theory is the study of computational effort required to run an algorithm. For instance, the computational effort of addition is big O(n). This means that the effort of adding two numbers increases linearly with a size that means the digits of the number. The computational effort of multiplication is big O(n) square. The effort increases by the square of the number sizes. These algorithms are said to be solvable in polynomial time, but these problems are comparably simple. In contrast, the best classical algorithm for solving the problem of factorization, that is finding the prime numbers of a number, is big O e to the n to the third. It means that the effort increases exponentially with a number of digits. Do you want to get a taste of this? Great. Try to solve the following factorization problems without a computer. 21. This is easy. 3 and 7 are the prime factors. How about this? 221. I'm out already, but maybe you have some ideas. How about this one? 2231. If you don't like my presentation thus far, just try to figure out this one here, the last. It will keep you busy until the end of my talk, at least. So now let's consider a polynomial task for a change. Multiply 3 and 7. That's easy. The next one, multiply 13 and 17. That's doable too. Maybe you need a pen and a paper for that. Multiply 23 by 97. It's getting harder, but you can probably solve this either by hand or with a pen and paper. And finally, multiply 101 and 223. Again, you see that each task is harder than the previous one, but you will be able to solve even the last one in your head or with pen and paper or with a small computer. This illustrates the difference between polynomial and exponential complexity. While your smartphone multiplies numbers with 800 digits in a few seconds, the factorization of such numbers takes about 2,000 years. Oh, sorry. The factorization of such numbers takes about 2,000 years on a supercomputer. But in 1995, Peter Shor, a mathematician, developed a quantum algorithm that solves the factorization problem in polynomial time. Sounds nice, right? This is huge. Modern cryptography builds upon the fact that it is practically impossible to factor these large numbers. If you can factor numbers in seconds, no secret is safe anymore. Apparently, we haven't experienced this apocalypse yet. Be assured, nobody can read your encrypted messages, except for the NSA maybe. The simple reason is that Shor's algorithm needs millions of error-corrected qubits to factor a number we're talking about. State-of-the-art quantum computers have around 100 qubits, and these are error-prone too. Even though IBM strives for a 1,000 qubit computer by 2023, the quantum processors we expect in the near term will remain relatively small and noisy. Nevertheless, in 2019, Google reported that their 53-qubit quantum device Sycamore solved the task in a few minutes that would take today's most powerful supercomputers thousands of years. So IBM, a major competitor of Google, of course, objected immediately. They argued that classical supercomputers could do the same task in 2.5 days, this one that Google claimed to last 1,000 years. But if you ask me, solving a task in minutes that takes a supercomputer days is still very impressive. Unsurprisingly, quantum machine learning made it onto the Gartner hype cycle in 2021. It is right here at the very beginning. The caption says that it will take more than 10 years to reach the plateau of productivity. You probably ask, hey Frank, if it takes another 10 years, why should I get started with quantum machine learning now? Of course, the limited number of qubits is a problem. But the 1,000-qubit device IBM plans to release next year is more than enough. The real problem is something else. The catch is that it's tough to do anything useful with its new computing ability. The problem Google Sycamore solved was particularly designed to prove a quantum advantage. It was a toy problem. It had no practical use. Technically, a quantum computer could do anything a classical computer can do too. Yet, if a classical computer can solve a problem, it's likely to be cheaper and maybe even faster to let the classical computer do it. Unlike classical computers, quantum computers need to be very precise. They operate close to the absolute temperature minimum because any heat could ruin a computation. You can imagine that this is not the cheapest technology to use. So the real challenge is to find these things that you should do with a quantum computer. These are the things that are intractable for classical computers, but worth solving. Critics doubt that there are any such problems. They argue that we would have found them if they existed. In reply, let me refer to history. There are deep parallels in how we first learned to compute. It starts with ENIAC, the Electronic Numerical Integrator and Computer. It was the first digital electronic computer that performed calculations more or less in the same way that today's microprocessors do. Built at the University of Pennsylvania, the US military implemented it in 1946. Back then, its only application was to calculate the trajectory of artillery projectiles. However, the Second World War was over, and there was little practical use for it anymore. They didn't know what to do with it. Yet scientists and engineers were thrilled at the possibilities that could follow. Undoubtedly, they were proven right. But in 1946, nobody thought of personal computers, laptops, cell phones, and the internet. These profound impacts of this new technology were the least anticipated. Instead, they're entirely derived from the access to this kind of computing technology. But we can't just go to an organization and ask, what's a really critical thing that's impossible for you to do? But if you don't do it, your organization is going to be in dire jeopardy. Because the answer is that there are no such problems. If an organization had those sort of issues, it stopped them from having an organization. So instead, we need people inside the organization who stretch and think about the sorts of computationally impossible things that could really be valuable to do it. And this is you. We don't need another physicist thinking about an organization's problems in the lab. They won't come up with these things. Such insights will come from practitioners. We need domain experts who know how to harness these special quantum devices. The time is now to become one of those experts. The time to get started in quantum machine learning is now. But I want to be honest with you. Quantum computing has long been a field for theoretical physicists and mathematicians only. It still is. But with the advent of the real quantum computers and the availability of quantum simulators, quantum computing is moving forward from the tech labs to mainstream commercial use. This dramatic shift will affect which roles companies will hire in the future. Companies will hire quantum computing specialists beyond their research labs. They will have a demand for experts who know how to tap the computational advantage of quantum algorithms into real business advantage. And one of these fields we expect to profit the most from quantum computing is machine learning. Machine learning is already thriving in various sectors, from industry to finance, from self-driving cars to natural language processing. Yet, as I said, the state-of-the-art machine learning models become extremely complex and therefore hard to train. While the inability to deliver such models could cause the next AI winter, quantum computing could be the decisive factor to prevent us from such a scenario. However, using quantum computers to solve machine learning tasks requires sophisticated expertise. Of course, the requirements may differ significantly between positions. Certainly, you need abilities beyond those of the everyday Cletus. You'll need to know a lot about algorithms, but just knowing how to implement them is not enough. You will need to know how to tailor them to address your problem at hand. Furthermore, you need to know the problems you face when scaling the algorithm beyond simple examples. And you need to have a toolbox full of quantum computing expertise that allows you to address these problems. Usually, the question of whether you need a PhD in physics or mathematics comes up quickly. Scientific papers and textbooks about quantum computing are full of physical jargon and mathematical formulae. Even blog posts on quantum computing are loaded with math formulas and all these things. It starts with the first concept you encounter, the quantum superposition. Unless you hold a degree in physics or math, the first and natural reaction to this is to put it away. If you're not familiar with the direct notation used here, or if you're not used to working with vectors, then such a formula is as good as Egyptian hieroglyphs. Don't get me wrong, math is a great way to describe technical concepts. Math is a concise yet precise language. Our natural languages, such as English by contrast, are lengthy and imprecise. It takes a whole book of natural language to explain a small collection of mathematical formulae. But most of us are far better at understanding natural language than math. We learn our mother tongue as young children, and we practice it every single day. We even dream in our natural language. I couldn't tell if some fellows dream in math, though. For most of us, math is at best a foreign language. When we are about to learn something new, it is easier for us if we use our mother tongue. It is hard enough to grasp the meaning of a new concept. But if we're taught in a foreign language, it is even harder, if not impossible. Of course, math is the native language of quantum mechanics and quantum computing, if you will. Physicists and mathematicians discovered most of the stuff in quantum computing. So of course, they build upon the knowledge of their peers when they share insights and teach their students. It is absolutely reasonable that they use the terms they are familiar with. But why should we teach quantum computing only in its own language? Shouldn't we try to explain it in a way more accessible to the learner? I don't see a reason why students of other nearby disciplines should be restrained from learning the stuff. For example, why shouldn't we support a computer scientist or a software engineer in learning quantum machine learning? I've got a clear opinion. I believe anyone sincerely interested in quantum computing should be able to learn it. Of course, this requires a teacher to explain the complex stuff in a simple language, a language that might not be the teacher's native language, but the student's. This is the purpose of my book, Hands-on Quantum Machine Learning with Python. I aim to help developers, practitioners, and students like yourself to become quantum machine learning experts. I already published the first volume on Amazon and Leanpub. It is right here. Right now, my Kickstarter campaign for the second volume is running. In this second volume, you will learn how to solve current optimization problems on real quantum computers. We will deep dive into the variational quantum eigensolver and use it to solve combinatorial optimization problems. I plan to provide an online classroom in addition to the book. In this classroom, I will provide presentations, just like this one today. In these presentations, I will cover the material of the book. But of course, the presentation part is not the key benefit of the classroom. I don't know how much fun it is or it is not to listen to me. Anyway, the benefit I aim to provide is the interactive part of the classroom. In that part, you will have the chance to ask questions, to come up with suggestions, and bring the problems you struggle with. I can't promise to know all the answers and have all the solutions, but I believe that it is much easier to master the challenges if you can ask questions and get feedback instead of solely reading a book on your own. An interactive discussion is a great way to learn a new topic and to get in touch with all the other interested colleagues. Either way, I want to thank you for your time and for your interest.